And now I'd like to move on to the portion of class where we review for exam 3. So the two main topics are conservation of momentum and conservation of energy. Um, Conservation of momentum is that if there's an interaction between objects where there are no external forces, then the total momentum is constant. Um, so you can add up all the momentum before something happens, you can add up all the momentum after something happens and set them equal. The thing that should signal to you to use conservation of momentum is whenever you have a collision or explosion. Because during that event, the forces involved in things colliding or exploding are so overwhelmingly large that other forces don't really matter. The other thing that's important to remember is that momentum is a vector. So if you've got a collision happening in two dimensions, like the pool balls or the ice skaters that we talked about a bit ago, you will need conservation of momentum separately and independently in X and Y. If there are any questions, stop me and type them in chat. Otherwise, I would like to. I have a couple of problems that I want to set up at the end. Megan asks, how can you tell whether momentum is conserved or not? Momentum is conserved if there are no external forces that are important. So momentum is conserved if there are no external forces. Whoops. Get off this tool. So another way to say that is if you've got a collection of objects that only exerts forces on each other, like the ice skaters, right? In the uh, horizontal directions, like if you consider y to be up in the air, in the x and z directions, those ice skaters are only pushing on each other. They're skating without friction. So whenever you've got objects exchanging forces only between themselves. So another example is um, if you have a solar system with only one planet. So if you've got the Earth going around the sun and the other planets aren't there, then really the only force on the Earth is the sun's gravity. The only force on the sun is the Earth's gravity. Could I give you a list of external forces? No, I cannot, because you have to think in each situation. But what I can do is I can tell you another situation that's going to be 99% of what you'll see. During a collision or explosion, the forces involved are enormous. Yeah, Megan, this is a great example. In the firecracker problem, there is a y force, always, gravity. But at the moment when that firecracker explodes, the forces involved in that gunpowder going off, yes, exactly, Shamil. The forces involved in that gunpowder going off are so overwhelmingly larger than the weight of the firecracker that you can ignore them. So the thing that you should write in your notes and put a little star on them is that the thing that signals to you to use conservation of momentum in a problem is whenever you have a collision or explosion. 99% of the time, that's going to be the time when you should use conservation of momentum. So Megan and Gilberto, does that help kind of in understanding when to use conservation of momentum? Like it really is as simple as things are colliding. Okay. For the work energy theorem, I have one more slide. Uh, I wrote these last night and I added this one at the last minute and I forgot that I had. We characterize collisions in three different ways. In an elastic collision, things bounce back so that the kinetic energy at the end is the same as the kinetic energy at the beginning. So if you ever have an elastic collision, I know there's one on the practice exam because I wrote the problem. Um, this means you're going to have a system of equations. So one of them is that the momenta before and after are the same. And the other one is, it's a terrible sigma, that the total kinetic energy is the same before and after. Should we be known to use conservation of momentum when there isn't an explosion or collision? Um, Occasionally that will happen, but that will only happen if you have objects with no external forces acting on them. So if you have something sliding without friction, there's an example on the practice exam, which is the example I gave you a moment ago, where you have a solar system with exactly one planet in it. And there are no external forces acting on either the star or the planet because all that matters is the gravity between them. But those sorts of situations will be quite rare. We also have two other kinds of collisions, partially inelastic and fully inelastic collisions. In both of those, some kinetic energy is lost. And in a fully inelastic collision, the objects stick together. So they have the same final velocity. What is an example of partially inelastic? If I bounce a basketball on the ground. So if I bounce a basketball, it's going to come back up, but it's not going to come quite as high as it started, which means some kinetic energy was lost in the collision. Fully elastic collisions in the real world are mostly only in particle physics. But a collision between, say, billiard balls is very nearly fully elastic. Thank you all for your questions, by the way. Megan, Samuel, Nicholas. Yes, Nicholas, we will tell you, and we will say this is an elastic collision, just like we did in our homework. Now I want to talk about the work energy theorem. This is kind of the more subtle idea. So we saw that work is the change in kinetic energy, which we can write like this. Here, when I write W all, this is the work done by all forces added together. Work is the dot product between force and displacement. There are three different and equivalent ways to calculate what the dot product is. But you'll need to use one of them if you have a force that's not exactly in the same direction as motion. Remember, positive work, you're pushing on something basically in the direction it's moving and it speeds up. Negative work, you're pushing on something against its motion and it slows down. So remember that the cosine of angles greater than 90 degrees is negative. A big point to remember is that forces perpendicular to motion don't do any work. This is like the string in a swinging pendulum or the normal force on a roller coaster car sliding down a track. It's always perpendicular to the direction that you're moving in, so it doesn't do any work at all. The idea of potential energy is an alternative way to keep track of the work done by conservative forces. So we have formulas for the potential energy from gravity and from springs. Those are the only conservative forces we've encountered so far. Friction is explicitly not a conservative force. You cannot associate it with a potential energy. So we've got two ways of thinking about work and energy. And I'm going to write something up above here. Where we started was by saying 1/2 mv initial squared plus the work done by all forces equals 1/2 mv final squared. But since we've realized that conservative forces can be accounted for using potential energy, we can split the list of forces into forces that we think of as associated with the potential energy, and those forces where we're still calculating work in the old way. Um, these terms that I've written down, it's very helpful to do this, I find. It's very helpful with these problems to write down in words what all of your algebra means. And we noticed that if you take potential energy and kinetic energy and add them up, so if you think of potential energy not just as a trick to calculate work, but as a kind of energy in its own right, you get this relation. And this is what we call the conservation of energy. I have some amount of mechanical energy in the beginning. I add to it or subtract from it by doing other work on the system, and that tells me the amount of mechanical energy I have at the end. So this is conservation of energy. And we ought not to be surprised that the formula comes out like this, because conservation of energy is probably the bedrock principle of all modern physical science, and for that matter, life science. Um, so that is a whirlwind tour through all of our topics. Um, does anybody have any questions at this point? I have a couple of problems that I'd like to set up in our last 8 minutes. Sure, Nicholas, go ahead. We're waiting on Nicholas to type his question. Potential energy is work that gravity does. Yes, or it's a way of tracking it. So the work done by gravity is the force of gravity. Oops. The force of gravity times the displacement parallel to that force. And that's going to be equal to mg times how far I move down, right? But then if I split this term up, and if I put I can see, let me get my highlighter back out. This term goes with the initial potential energy, and this term goes with the final potential energy. So yes, you get the same equation regardless of whether you think about the work done by gravity or gravitational potential energy. All right, so I have two problems that I'd like to set up. Offense has a question. You know how you said that if there aren't any external forces, momentum could be conserved. Can you explain again why in the example from last week's lecture with the two people swinging after they push off each other, why wasn't the momentum conserved in the first part right after they pushed off each other? Yes. This is a really good example for us. So I'm going to get us a blank page, and now I need to push the buttons that make it blank. Paper background dotted. So this, here was the scenario you had. So in that question, you had two people, and my art is going to be terrible, please forgive me. We had two people hanging from strings, and these two people were sort of bad at social distancing. And they push off each other. So what the question asked you, actually, I just want to draw this over here further on the left. So here are two people. And the question said, okay, when they push off of each other, they're hanging from the ceiling, they're going to swing up at some angles. So they'll go out like this, up into the air. That's not long enough. Bloop. And the question asked you to figure out what that angle was, right? So the way that you know momentum is not conserved from here to here, well, momentum is not conserved if there is an external force. So what external force acts on these people while they're swinging through the air? There is so gravity, yes, gravity and tension. Both of you are right. Um, so gravity is changing their momentum in the y direction, and tension is changing their momentum in both the x and the y directions. So momentum is not conserved from there to there. Can we account by the work done or for the work done by all forces in that process? We actually can't, because calculating the work done by their hands as they push on each other, I don't know how to do that because I don't know like the distance that they extend their arms, right? Um, but what I believe that you had, um, these two might have been different angles. I don't remember exactly what you were given in this problem. It wasn't a problem that I wrote. Um, the way to approach this problem, the insight that I'm after here, is I can think of, these are terrible people, but you get my idea. Um, this thing here, going from this figure to that figure, this is like an explosion, right? I have two objects that are touching, and then they repel each other and push off. So since this is an explosion, how can I relate the first picture to the second picture? Remember, we have a technique that we use for collisions and explosions. What is that? Momentum. So here, relating the first picture to the second picture, this is conservation of momentum. And now, in going from the second picture to the third picture, what technique should I use? Conservation of energy. Yep. So in all of your problems, one of the things that you'll need to do is to think carefully about and draw cartoons like this. To say, okay, I've got this cartoon in the beginning, this cartoon in the middle, this cartoon in the end. What techniques am I going to use to relate what happens in one cartoon to what happens in the next cartoon? The things that I had prepared on my next two slides um, were basically just doing this for two other scenarios. Um, I can do those if you like, or I could answer a few more questions. Class is kind of nominally over in 15 seconds, so anybody who wants to head out can. I'm going to stay in this Blackboard Collaborate for 5 more minutes if anybody has any questions, and then I got to go through the other one. Thank you all for your attention, your hard work. I know you all are working hard for our class, and I appreciate it. I'll see you all later. See you in office hours tomorrow from 8 to 10, um, or in your recitations. I'll be watching chat if there are any more questions. Thank you, Max. How do you know if you need to draw more than two? Uh, AM, Vincent. So office hours tomorrow for me are 8 a.m. to 10 a.m. The point is that's 8 p.m. to 10 p.m. in East Asia. So we want to make sure our office hours are accessible to folks who are on the other side of the planet. Martina asks, how do you know if you need to draw more than two? So this is a situation, I call these kind of collision plus something else problems, or explosion plus something else. Let me give you an example that's my next one, Martina. So here I've got a train car rolling down some hill. At the bottom of the hill, there's a locomotive at rest with its brakes engaged. When the two cars collide, they stick together and slide a distance d before coming to rest. So here, in this problem, you actually need 4 pictures. Because conservation of momentum, we know we need conservation of momentum because there is a collision, right? So my art is going to be terrible. So I'm starting out with a train car up here. We'll make it a different color. So I'm starting out with a train car up here, and I have another one at rest down here. And I know my ending cartoon is gonna be like this, where the two cars, the blue one and the orange one, have stuck together and they have slid a distance d. But I know that conservation of momentum only gets me from right before the collision to right after the collision. So I know that I need an intermediate step, right? This will take me another 2 minutes to draw if anybody has classes after this one. So here, I know that right before the collision, so this is a split second before the collision, that one's not moving, but this one's moving. I'll call this VA that way. And conservation of momentum will let me relate that to what happens right after the collision, where the two of them have stuck together. They haven't moved together yet, but the two of them are stuck together, both moving this way together at VB. So in this problem, remember, conservation of momentum only gets me from a split second before the collision to a split second after the collision. So getting from this picture to that one is conservation of momentum. But there are no collisions happening as the thing slides down the hill. So Martina, you're the one who asked, what technique can I use to get from picture 1 to picture 2? That's energy conservation, exactly. And what about from picture 3 to picture 4? Again, work energy, which is the same idea. So Martina, does that help answer your question? Yeah, drawing, it's almost always whenever you have a collision and something else is the insight there. Yes, Samuel. So Samuel, you're thinking again about this problem? Yeah. Yeah, exactly. Momentum is conserved here, but here it is not. All right, I have to hop into the other Blackboard Collaborate session to run that class. Yes, Martina, when I say work energy, because remember, the work energy theorem is just another expression of energy conservation. That was the idea from here, right? This is the work energy theorem without thinking about potential energy, but with potential energy, it's equivalent. All right, I got 4 minutes to go to the other class. Yep. Thanks, Martina. Thank you for all your amazing questions. Keep asking them. And I will see you all later.